Good morning, everybody, or very early morning for our Japanese colleague. And no, yeah, no, it's a late afternoon, late afternoon. Beg your pardon? Okay, there is an echo. Okay, so welcome. I'm Gérard. I'm from Grenoble, France. I'm sharing this morning session about modeling and evaluation. And so I really invite, in fact, the author of the first paper, multi-scale spectrogram modeling for neural text-to-speech, to take the floor. So Ammar Abbas is there. Who is giving the talk? Alexis?
Yes, sorry, I was trying to figure out the unmute button in Zoom.
Okay.
Yes, I will be presenting.
Okay, so it's a great family of Alexa. Okay, so
exactly.
Please. Yeah.
Good morning, everyone. So yes, the main contributors to the paper were Ammar, Abbas, and Bajibabu Bollepalli. They're not attending SSW, so I will be presenting today. I see someone on the screen. Is everything all right? Yeah, okay. And yes, so I will be presenting our work in the Amazon text-to-speech team on multi-scale spectrogram modeling for neural text-to-speech. So the goal of the research was to see if we could synthesize speech while improving the prosody by going through several levels of generation of the spectrograms. So we would predict a rough approximation of the spectrograms that captures speech information at the level of that rough approximation, use that approximation, pass it to the next layer. The next layer will predict a finer version of the spectrogram, and so on and so on. Now, what we call a scale, there are two axes in a spectrogram, the time axis and the frequency axis. In our case, we focused on the time axis, so the linguistic part of the spectrogram, and we split at the level of frame, so normal spectrogram as we use it normally, phoneme, word, and sentence level spectrograms. So from now on, whenever I will mention a model that I called word level model, it's a model that encompasses layers at frame, phoneme, and word level. And when I will say sentence level, I mean a model that represents the spectrogram at the frame, phoneme, word, and sentence level. Spoiler alert, our results showed that the word level approach performs statistically significantly better compared to our baseline and compared to the sentence level model on 2 American English female voices. Now to get into the model, the baseline is what we call Durian Plus, which is a model we presented at ICAS this year, which is a modified version of Durian. So Durian is a neural text-to-speech sequence-to-sequence model that uses a duration model instead of attention to transfer the information between the encoder and the decoder. The duration model is very similar to what was explained yesterday by Hail in the other Amazon paper about duration model. The encoder is the same kind of encoder that we can find in tacotron models, and the decoder is an autoregressive decoder, again, similar to tacotron, but it does not have a postnet. As we explained in the paper, in the case of a duration-based model, and in the case of the model we were training, adding a postnet was making the model very unstable, whereas removing the postnet gave correct quality that was similar to what you find in an attention-based model that has a postnet. So there was literally no reason to use the postnet. For the vocoder, we use a wavenet-like model. Now, what we're going to do in the multi-scale model is that we replace the decoder, so the block at the top of the phoneme embeddings, with a multi-scale decoder. And that's about it. That's the extent of what we've been doing. To train the baseline and to train our model, we use forced alignment to extract the durations. So our forced alignment between the text, the phoneme sequence, and the audio to find the duration of each phoneme and pause. At training time, we use those real duration to train the decoder. At inference time, we use, of course, the synthetic duration. Duration to synthesize the spectrogram. The decoder being autoregressive, it needs the spectrogram at the previous iteration to predict the next iteration. So at training time, since we don't want to have a very, very slow training where we would predict each spectrogram and pass it back, we use the original spectrograms as a T-1 input to the decoder, so what we call teacher forcing. I didn't forget anything, nope. So no, when we replace the decoder with a multi-scale decoder, basically we replace one decoder with L decoders, depending on how many scales we have. In the case of the word level decoder, we have 3 scales. In the case of the sentence level decoder, we have 4 scales, which correspond to what is being shown here. So the first step is to take the real spectrograms, and for each level, each scale, compute the average spectrogram. So for instance, at the sentence level, we take the whole time domain, the whole frame level spectrogram, and we compute the average spectrum. So one frame, which is the average of all the frames. At the word level, we take the piece of each piece of spectrogram that aligns with each word, and we compute the average of all these frames to get one frame that represents the word. At phoneme level, same thing, the average of the spectrogram for each phoneme. At the frame level, we use the spectrogram as it is. To decide how, well, the spectrogram that corresponds to the sentence is quite easy. You just take all the frames. To decide how the spectrogram aligns with a given word or with a given phoneme, we use the first alignment that are also used to train the duration model, so that given those alignment, we know exactly which frame belongs to which phoneme and which frame belongs to which word. So it's relatively trivial to compute the average spectrogram for each level. And so the end result is that at the scale of the sentence, you will have 1 frame. At the scale of the word, if you have 10 words in your sentence, you will have 10 frames. At the scale of the phoneme, if you have 80 phonemes, you will have 80 frames. And at the scale of the frame, if you have 1 second of signal, let's say 10 seconds of signal, you will have 800 frames. The loss function that we used was the Euclidean distance between the spectrogram that was predicted at each level of the decoder and the spectrogram, the average spectrogram that had been computed in the step I just explained. So in terms of related work, there are 2 work mostly that have done part of what we're doing here that are kind of similar to what we're doing. There is Chive, where the goal of Chive is to encode the prosody in a vector that represents the prosody of the sentence, and it does so in a hierarchical way. So it starts at the frame level. From the frame level, it compresses at the phoneme level. From the phoneme, it goes to the syllable, then the word, if I'm not mistaken, and then represent the whole sentence in the whole prosody of the sentence in one vector. That's the encoder part. And then there is a decoder part, which is the inverted hierarchical representation. So it goes from that sentence vector and it tries through the same steps, so word level, syllable, phoneme, and then eventually frame level to reconstruct the prosodic features such as F0, energy, and I think duration. So in that sense, the hierarchical aspect is there. On the other hand, it's trying to represent only the prosody, whereas in our case, we represent the whole spectrogram. So there is also phonetic information being used to build the average spectrogram and to reconstruct them at inference time. The other difference is that we do it, with spectrograms. Anyways, The second paper is Moinet, more specifically the multi-scale part of Moinet. So what the paper Moinet does is basically consider a spectrogram as an image, like it's two-dimensional, and we visualize spectrogram constantly, so there are images. But it doesn't take into account what is in that image. So the fact that that image represents speech, so that there is linguistic information to be taken into account. So basically it does a multi-resolution thing, but with a fixed step. Like it will divide, for instance, the frequency axis in 2, then in 4, then in 8, then in 16. Likewise, over the time axis, it will not take into account words or syllables or phonemes. The second difference is that it's attention-based, whereas our model is like child duration-based, and it uses a mixture of Gaussian to represent, from which it samples to generate the values of the spectrogram. Now, how it looks like at training time and at inference time. There is an example here with phoneme level and word level. So you can see, for instance, there were 28 phonemes in the original sentence. We computed 28 averaged frames. The darker lines are the silences between words. At the word level, they were in the same sentence, there were 6 words. So you got, again, 6 frames, one to represent each average spectrogram for each word. And then on the right side, you can see the predicted spectrograms, where you can clearly see there is oversmoothing going on compared to the Oracle spectrograms. But as we will see later, even though that oversmoothing is there, we still get better result than without the multi-scale approach. But still, that's something to improve in our system. So we did different types of evaluation. So first we did a kind of mushra. Strictly speaking, it's not a mushra because the testers were not presented with the recording. So it's more like a 3-way comparison preference test. We compared the baseline, so the REN+, the sentence level multiscale, and the word level multiscale. So basically the difference between sentence level and word level is that there is one extra level, the sentence level, in the multiscale, in the one in the middle. The sentence level model was not better than the baseline. The word level model was better than the 2 other model with a p-value that was at like 10-6 or 10-7. So that's one thing we had. This was done on a single voice, so an American English female voice. There were 50 utterances tested by 24 native listeners, and this was done with a third-party contractor, so not through crowdsourcing. Knowing that the word level was better than the other 2, what we did next was the preference test to A, confirm our result, and B, try on another voice, because preference tests are cheaper than mushra. So on the speaker A, which is the same as before, we got confirmation of our results. Again, this was done with a third-party contractor. Basically, the word level model is preferred over the baseline significantly. Then we tried with another speaker, speaker B, but this time we used crowdsourcing. And there we got no significance. But we also noticed that there were likely cheaters in the test because for 2 reasons. The sentence were around 10-15 seconds long. So you have 2 systems, so it should take 20-30 seconds to listen to the systems. Some testers were doing the test in 2 seconds per pair. So like 1 second for each, which is basically the time it takes to press play, move the slider, press play, move the slider, select one of the 2 and submit. The other thing we noticed is that some testers were always selecting the same system in the interface. So they were basically always selecting system 1, system 1, system 1, system 1, except we randomized the test. So they were randomly picking one of the 2 systems. They didn't actually do anything. So there was a weird pattern. We cannot be 100% sure they were cheating, but there are strong indication that they were cheating. If we remove those testers, we do have significance. But if we remove those testers, we remove about 80% of our testers. So we're not confident enough to affirm that our results are significant, but on the other hand, there is something to be improved there in the protocol and in the selection of the testers in the future. Since then, we've done a bit more testings, and we got some significant results for speaker B with different experiments. But again, we're still looking into it. So I'll play a few samples now and then conclude.
How are you on this fine and lovely day? How are you on this fine and lovely day?
Can you confirm that you can hear this? I cannot see the chat, just in case someone has put yes in the chat. Okay.
Yes, we can. Yes, we could hear it.
Perfect. I'll continue.
Around 11:45 p.m. Around 11:45 p.m. Whatever happened to journalistic integrity? Whatever happened to journalistic integrity?
So in conclusion, I presented a new multi-spectrogram, multi-scale spectrogram modeling approach, where the multiple scales are decided based on linguistic information. The scale that goes from frame, phoneme, and word level shows statistical significance preference over our baseline for at least for sure one speaker, and we seem to see it for another speaker. In future work, of course, the obvious one is to add multiple scales along the frequency axis. So add the extra step that is in Moinet, add the syllable scale so that we can model better, hopefully, stress and intonation information. Add layers, linguistic information on top of word level. So something like a group of words or phrases, then revisit the sentence level model for which we didn't have significant results. And then further ablation studies, because so far we've been looking into sentence level versus no sentence level, and that's about it in terms of ablation. And that's it. So, chat.
We can perhaps start the series of questions using the remote participants. I don't have a list, so how you have this? Okay, the chat.
I can see the chat. So the first question seems to be by Marcel. Capture effect of accent. One may assume. Okay, I will read it out loud then. Assuming that the word level mass spectrograms can capture effects of accent, one may assume that the same approach could also work well on the syllable level to capture effects of stress with regard to the F0 variation in the mass spectrogram. Is this something you have tried or would consider try out? So yeah, as I say, that's in the future work. The crowdsourcing platform. I think it was Crowdflower, but I'm not 100% sure. I'm checking because I have the paper just next to me, but we didn't mention it. I think it was Crowdflower. When you remove the cheaters, how many listeners does that leave? So we had 48 listeners from the start, and when we removed around 80%. So I think we were left with 9 or 10 testers, which is below recommendation of having at least, if I remember, 20 to 30 testers. So that's why we're not very confident in claiming that we have significance when we remove all the cheaters. Javier's question, good morning. We can assume that the main advantage of the word level should be in the prosody, right? That's correct. Sorry, I got lost. Previous study on this type of hierarchical prosody usually showed that the most useful level is the syllable in English level, where there is large number of monosyllabic words. Could this have taken words as a kind of proxy for syllables? Yeah, that's a very good point, especially given that we were working on English. I cannot answer until we have tried the syllable scale, and the reason for which we didn't do syllable scale was mostly practical, that getting the information was much more complicated than having the information.
First point of your perspective, so
yeah, for us it was more complicated to get the information with our tools. Yes, Marcel. Simon, as you say, the spectrogram captures phonetic information. So what is the motivation for modeling word level average phonetic information? So that's in line with what Javier said. For the word level, the main expectation was about the information about prominence and average energy pitch and possibly pitch rising or falling. So global trend of the pitch over a word rather than localized trend that you have at the phoneme or syllable level. Click worker, yes, correct, Thomas, thank you. I always get confused, not crowdflower. 100% sure, okay. Simon, we are very happy with Prolific. Very low % of cheaters, low effort participants, so that's something we
and it's
consider.
Recommendations.
Yeah.
So any question in the from the locals? If not, I have 2 questions.
Yes.
First, it's a technical question or a subtle one. So the encoder is not aware of your decomposition.
No, it's well, it is through the backpropagation at the training time. Like the output of the encoder is input into the decoder. So when you apply the backpropagation at training time, the encoder, the backpropagation goes down to the encoder, but the encoder there's not an autoregression taking whatever happens in the decoder and inputting it back into the encoder, if that's the question.
Okay. So it could be worth for examining this. And the other question is, in fact, you see an improvement, but this improvement is maybe caused by the excess number of parameters, because each time you had a new level, you had new 3 parameters, in fact, in your system. So your size of your model increases.
Yeah. Yes.
So
I see your point, and that's part of the evolution study we have to look into. Yes. Sorry, I skipped a question apparently. Did that answer your question? I basically agree with you. But I don't have data point to tell you. We haven't done this evolution study yet, so I can answer further.
Yeah. It could be interesting, at least in the papers, to have a number of 3 parameters of each model, because you are dealing with billions of parameters, and it could be interesting just to have a look. So, Javier. You also answered to the question because you are planning to have a frequency decomposition in the future. So
yeah, but frequency decomposition at this stage would still be splitting the MEL spectrogram into bands, into groups. Let's say if we could call bands, it's bands of bands, which is a bit weird. Ravier's question is more going towards something like what Shive does, which is using C0 and F0, for instance, as modeling. That's not something we are considering at the moment, because eventually we have to put all of that into the vocoder. However, we have another paper where we do what we call multitask modelization, where F0 and Capstral coefficient are intermediate features that are predicted. But we're not yet doing that kind of thing in a multi-scale manner. The encoder outputs at frame rate, which is upsample to frame rate, correct? Then average back down to linguistic units. Is that correct? Yes. It's not average. So from the phoneme point of view, we use LSTMs to compress or average, as you say, back to the level of linguistic units. So for instance, sentence level will pass all the phonemes embedding through an LSTM and take the last hidden state that will represent the sequence of phoneme. For a word, we will pass the sequence of phoneme from that word into an LSTM, and the last hidden state represent the phonetic content of the word. So it's a form of averaging, but more complicated than just taking the average value. And then, yeah, Rians recommends Prolific as well. So it's definitely something we have to look into. Yes.
Okay. So I think we are done. Thank you very much.
You're welcome. Thank you.
Okay, so thank you. So the second paper is how do voices from past speech synthesis challenges compare today? And it will, I don't know, the presentation will be given by Erika or Junichi?
Hi, I'll give the presentation.
Okay, Erika Cooper. So please, take the floor.
Okay, can you see my slides?
Yes, we can see.
Great. So hi, everyone. I'm going to be presenting our work. How do voices from past speech synthesis challenges compare today? So a quick overview of the talk. I'll be introducing the project. I'll describe our listening test, which was the main center of the project. I'll describe the results. Our listening test also enabled us to do some analysis of natural speech, and then finally discussion and future work. So this project was a very large-scale listening test combining samples from many past Blizzard challenges and voice conversion challenges. So the reason why we did this is because master results from separate past listening tests cannot be meaningfully combined to each other and compared, because the set of systems and therefore the context of the test are completely different. So in a given listening test, the best system and the worst system may be better or worse than the respective best and worst systems in a different listening test context. So conducting a new test with all of the samples combined together will enable more direct comparisons. And the data that we gather can be used also to train hopefully automatic loss prediction models, which is out of the scope of this project, but it's our ongoing and future work. So some research questions we were interested in are: how reliable and reproducible are MOS scores? How do past listening test results compare to ratings gathered in the present day? Will the results correlate even when the listening test context has changed? What observations can we make about speech synthesis and voice conversion systems over the years? What are the effects of speaker of the data set on synthesized speech quality? And also a sort of outcome of this research is a very large scale database of a variety of synthesizer outputs and their MOS ratings from the same listening test for the purpose of training MOSNet-like systems for automatic MOS prediction. So next I'll describe our listening test setup. So we had 187 different systems from past Blizzard Challenge, Voice Conversion Challenge, and also ESPNet TTS, which is a nice open source toolkit for TTS that in ICASP 2020 trained a bunch of TTS models on the LJ Speech dataset and released their samples. And Blizzard Challenge and Voice Conversion Challenge also have released their samples and listening test results for some of the years. So to sort of keep things sort of consistent, we picked samples from English hub task only for Blizzard Challenge. For Voice Conversion Challenge, in the most recent challenge, 2020, there was a same language and a cross-language task, but we picked same language samples only. We chose 38 utterances per system, and we balanced samples over genre, where there were different genres in the data. We balanced over all combinations of source and target speakers for the voice conversion samples. And only genres included in the original naturalness tests are included. So for some of the Blizzard challenges, there were things like semantically unpredictable sentences, which were used for intelligibility testing, but not naturalness testing. So we excluded those from our test for naturalness as well. So our test design is basically, we have sets, and a set is just basically one survey that a listener can take. And each set contains one sample from each system. So that's 187 different samples. We recruited 8 Japanese listeners per set for a total of 304 total listeners. And the task they were asked to do was a MOS rating for naturalness on a scale from 1 to 5, incremented by 1. So next are results. So it was a lot of results. I'll just try to give a high-level description of this. So this is kind of like a histogram of the results sorted from lowest average MOS to highest. Showing the frequency of how many times each score was chosen for a given system. These are the system IDs, and the ones in red are voice conversion systems. The ones in blue are text-to-speech synthesis, and the ones in black are natural speech. So this kind of follows a pattern that you might expect. These are sorted, by the way, from low to high. So interestingly, for the best systems, 4 out of 5 of them were ESPnet ones, and the 5 worst systems were all voice conversion ones. But let's remember that the voice conversion challenge typically has a smaller amount of data that is provided to participants for training, so this is expected. We also looked at listener agreement. So we had kind of moderate agreement at 0.5 for both Krippendorf's alpha and interclass correlation. So on the left is the 10 systems that had the highest standard deviation of ratings, and on the right is the 10 systems with the lowest standard deviations of scores. So the most agreed upon systems are the worst ones, and also natural speech. So that's expected. And then we see on the left for the more kind of like controversial systems that people kind of put, you know, all over the range of scores. ESPnet's Merlin baseline that they trained on LJ speech actually had this almost kind of flat distribution of scores. So to address our first research question, do new MOS results correlate with the original ones? So we looked at system level and utterance level Pearson's correlation coefficients, Bierman rank correlation, and root mean squared error between the original and new listening test results by challenge or by set of systems. And we can see at the system level, we see very nice high correlations at around 0.9 or higher for most of them between our listening test and the original results. At the utterance level, we see slightly lower kind of moderate correlations. And root mean squared error kind of shows that so this has kind of a range of values, and this shows that even though we get high correlations for the between the two listening tests, the absolute values of the scores themselves may differ, and this kind of shows the effect of the different listening test context. So next we can look at whether MOS scores improve year by year. So we can look at the best, so this table is showing the best system in each challenge compared to the previous challenge's best system. So we can look at the MOS score, whether it improved since the last challenge and whether the difference is significant. And for Blizzard, 2010 was the only year that this happened. For voice conversion challenge, you can see more improvements year by year, although the difference was not significant between 2020 and 2018. So maybe a more, so we have some confounding factor that I'll discuss later, which is the fact that the database or the speaker of the data for each Blizzard challenge differs from year to year. So maybe it's better to look at whether each year's best system is significantly different from that year's natural speech. So we can see as we move forward through time, the best system is not significantly different, and same for voice conversion. And for Blizzard, this started in around 2010. So here's another sort of view of that. We can look at the difference of each system from natural speech. And we kind of want to factor out the strong listener preferences. Maybe some listener really likes or dislikes that year's speaker. So what we did here was for each challenge, we z-score normalized each listener's ratings, and then we got average ratings, normalized ratings per system, and then we say what's the difference from natural speech. So this top row of dots here is natural speech, and the other dots are the systems. So you can see the the best system, so 2010 has an unusually good best system, but aside from that, overall, you can kind of see the increase year by year as the best system approaches natural speech. And you can also see that more systems are kind of moving up into this upper range here. So next, we could also look at correlation with objective measures, because it's nice to see if we have some objective measure that can predict mass. And we found very kind of low or non-existent correlations with the objective measures we tried. We tried signal to noise ratio, P563, and MOSNet, a MOSNet system trained on ASV spoof. And so we think there's a lot of room for improvement of objective measures that can predict mean opinion score. So next we could take a look at, in our MOS test, what kinds of preferences listeners had for the natural speech, so for different speakers. So the effect of speech corpus on perceived TTS quality is well documented. And since every challenge uses a different corpus, as I mentioned earlier, this is a confounding factor, but it's still important to capture preferences regarding these speaker preferences if we want to do something like train a MOS prediction model. So we had some metadata about our natural speech, so such as whether they're a professional speaker, their dialect, and genre, and so on. So we found that professional speakers were rated as significantly more natural than non-professional speakers. We found that female speakers had a marginally significantly higher MOS than male speakers. We found no significant differences between British and American speakers. And as for the genres we had labeled were news, book, and conversational. News was rated as most natural. Conversational was a little lower, but not significant. And book speech was significantly lower. So we also looked at speaker characteristics. We extracted standard prop features such as minimum, maximum, mean, and standard deviation of F0 and energy, noise to harmonic ratio, jitter, and shimmer. And we didn't find any strong correlations for these, but we found moderate negative correlations with MOS for shimmer, noise to harmonic ratio, and mean energy, and moderate positive correlations with MOS for standard deviation of energy. So a nice characteristic of the Blizzard challenges is that they each have, every year there's 2 benchmark systems. There's a festival unit selection system, and there's the HTS HMM synthesis system trained on that year's data. So every year the festival system is exactly the same, and the HTS system is that year's HTS system. So it's a little different, but we think it's kind of similar enough that we can include it in this comparison. So year by year, we looked at whether how festival and HTS samples correlated, their MOS scores, how they correlated with that year's speaker. And we found more moderate correlations for festival and strong correlations for HTS, which shows us that the HTS output quality tracks more closely with the quality of the training data. So finally, some discussion in future work. We now have a nice large data set for training MOSNet type systems for predicting mean opinion score. We found, this is reassuring that we found strong correlations with past listening tests, even in a different kind of context. We found that the choice of speaker for training data is very important. So we want to see whether repeating the test with English listeners will reveal language dependent or cultural factors. So for voice conversion challenge, they ran a listening test with both Japanese and English speakers and found very high correlations. But for some of these factors, like genre, where book speech was less preferred, we wonder, for example, whether that's somehow cultural or language dependent. We found that some systems have very clear agreements, where others have a much wider distribution of scores, such as the Merlin system. So we're wondering what makes certain systems so controversial. Are certain types of artifacts or unnaturalness more salient to some listeners than to others? So we really want to do more analysis. We didn't do any analysis of listener differences, but we definitely want to do that as future work. And since we have 8 ratings per system, we think we can incorporate the variance of scores into MOSNet in addition to the mean just by itself, because knowing how much people disagree is also useful information if you're trying to analyze your TTS system. So that's all for this talk. I think we can answer some questions.
Thank you very much. So very, very nice piece of work. I think we need something like this every 10 years. So any questions from the outside? So do you think there is improvement over the years that is in fact a result of listeners getting used to synthetic speech as it's more common in products? So,
yeah, that's a really good question. Yeah, I think something we might consider doing is, so the demographic data we have for the listeners are their age range and their gender. And I think something we may want to include in a future test is to ask, like, how often do you listen to TTS? Like, do you use it for your GPS, or do you use like, one of these home assistants or something like that, to see whether that affects their ratings or not.
So the data was read speech almost every year, right? Could this
That's right.
be the reason? Yeah. Could this be the reason why professional speakers are judged more natural than non-professional? Maybe naturalness is actually fluency.
Yeah, so it might also be having to do with recording conditions. So for example, for the LJ speech data, you can hear kind of like some reverberation in the background, and I don't know whether listening test listeners take this kind of thing into account or not. But I think that might also be a factor.
We have shown that there are several dimensions in the judgment which are hidden by just a unique number, a most number. Yeah, sure. Any question in the room? Yeah, please come.
Thank you. Congratulations for the project idea. And my question is, have you tested the English competence of the subject? And is there any correlation there or dependence on the English competence and the evaluation?
Yeah, we didn't. And that would be another interesting kind of piece of demographic data to collect. We didn't actually require listeners to understand English at all, but we might guess that some of them or many of them do. And yeah, I think that may affect their ratings in some way.
So how did you determine the number of listeners required?
That was well, we wanted at least 5, and so we had a budget for that. It was kind of a boring practical reason. We had a budget, and so that we said, okay, how many utterances can we pick, and then how many listeners, and then what's sort of a good balance of those. So yeah,
just a very small question. So depending on the years, there are not the number of systems tested vary.
Yeah, that's true.
And, did you have any insight of it is in fact the accuracy of the judgment according to the number of systems tested? Because if you are in a mushra, you have a strong impact of a number of judgment you have to perform for a unique sentence. So perhaps the fact that you have you are very homogeneous according to the systems, but the judgment of each sentence differ. It's perhaps because each year you have a different number of versions to rate, and when you have, I don't know, 10 versions to rate, you are perhaps less precise or clean when you are as a rater. What do you think?
Yeah, I think, well, I guess
interesting to have a correlation. Yeah.
Yeah, I think this is an interesting question for sure. And I don't have an exact answer. I would say that the listeners don't know how many different systems there are necessarily, but they do have, a different number of samples they have to hear. And I do kind of wonder about stuff like listener fatigue when there's like 187 samples. So it may be interesting to look at, if we can see any sort of pattern as they do the test. Do ones towards the end of the test, have less variance or less agreement with the other listeners or something like that.
So, and you have we have a suggestion of a workshop dedicated to evaluation. So it's a good point because so I'm likely to organize the next one, so Grenoble. And so we have already discussed this, and I think it would be very interesting to have in the next speech synthesis workshop a session or a group discussion really on this evaluation issue. Because as we said, systems are beginning to be more and more acceptable, and so we need to have a better insight of what are the dimensions we want to explore and to test. So yeah, it's a good suggestion. Perhaps not a whole workshop, but at least a long discussion, good discussion about this.
Yeah, for sure.
Day. Yeah.
Yeah, I see a lot of papers in this workshop about this topic, and I think it's we're all thinking about it. It's very important.
So in 2 years' time, you will be invited as a guest star. Okay. So thank you very much.
Thank you.
Good luck for your work. So the next paper is accent modeling of low-resourced dialect in pitch accent language using variational autoencoder. And the presenter will be?
Hi, I'm Kazuya.
So Kazuya or Tomoki or no?
Kazuya is, I am the
okay,
presenter.
So the first offer will be presenting. Are we in time?
Okay,
so perhaps we just wait 2 minutes to be on time.
Okay, thank you. So I'll start. Thank you for the introduction. Hi, I'm Kazuya, the University of Tokyo. Today I'll talk about
just wait 2 minutes so that
okay.
we are just on time if somebody is connecting.
Thank you.
No, sorry. Do you have something to listen to so you can check the sound? Could you check the sound or you are?
Okay, then I will.
Samples. Do you listen? Do you play samples?
Not in the slide, but.
Okay, so you are safe.
Thank you.
I said you can start. Okay, sorry.
Okay, thank you. Okay. Today I'll talk about a framework of TTS for low-resource dialects of pitch accent languages. Text-to-speech for dialects are useful for personalized TTS. For example, it will be a good alternative voice output for these healthier patients who can't speak anymore but still want to communicate in the dialects. It'll also be a good tool for local mascots to speak in the local dialects for a higher quality of entertainment. In reality, however, TTS of dialects are difficult to construct because of resource problems such as speech data, a lack of speech data, labels, etc. The bottleneck varies depending on the language, since dialects appear differently in different languages. In this study, we focus on the Japanese dialect. Japanese is a pitch accent language. Its pitch accent is defined as 2 class labels for each mora, namely accent labels for all dialects. For example, the above image shows the accent labels for 3 homographs hashiwa. The left, center, and right one means edge, sharp 6, and bridge, respectively. We pronounce them as hashiwa, 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 like this. Depending on the dialect, this label changes. In the Osaka dialect, for example, the accent labels for these phrases are defined as below. The Osaka dialect speakers pronounce them as hashiwa, 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 which are completely different than those above. And these accent labels are known to be necessary for natural Japanese TTS, even for an end-to-end system. The reason why is that without accent labels, the homographs would have the same input sequence, even though they have different pitch accents, which obstructs stable training. So we have to prepare the accent labels of the input text, both to train the acoustic model and to synthesize speech samples in inference. So how do we prepare them? In the standard Japanese CTS, namely for the Tokyo dialect, two methods are popular to prepare accent labels. First one is using accent dictionaries. Since the accent labels are summarized as a dictionary for the Tokyo dialect, we can use it for accent label annotation. Second one is hiring professionals to provide the labels to the text. However, these approaches are not available for other dialects because there are no accent dictionary for other non-Tokyo dialects and few annotators that are familiar with both of the dialect's accent system and the labeling method. So it is almost impossible to provide accent labels for non-Tokyo dialects. This is a crucial problem for natural TTS of Japanese dialects. So we should investigate the dialect TTS system under the condition that accent labels are not provided. The purpose of this study is to propose a framework of accent modeling when lacking accent labels, since, as I said, accent labels of non-Tokyo dialects can't be provided because of low resource problems. In this study, we focus on the Osaka dialect. For accent modeling of the Osaka dialect, we think there are two major challenges. First one is that we have no accent labels in training, which will result in poor performing acoustic models. For this challenge, we can use text and speech samples for modeling. Second one is that we have no accent labels in inference, which will result in unnatural synthesized features, even with high performing acoustic models. For this challenge, we can use only text for accent modeling. To solve these problems, we take the approaches in the slide. First, we propose accent extraction models with VAE for training. Proposed AEMs extract accent information as latent variables from speech samples by unsupervised learning, and extracted accent latent variables will be a good substitute for accent labels. Secondly, we propose accent prediction models for inference. Proposed APMs predict ALV from only the text. For APMs, we utilize also accent labels of the Tokyo dialect. The overview is shown in the slide. The AEM is based on an autoencoder framework. The encoder takes frame-level linguistic and acoustic features as the input and outputs moral-level accent variables, ALVs. The decoder takes the moral-level ALVs and the linguistic features and outputs F0 sequence. We call the part of the yellow box as TTS LV. In inference, we do not have access to the acoustic features. So APMs predict the moral-level ALV from the linguistic features. The APMs share the part of TTS ALV with AEMs. APMs predict the moral-level ALV from the linguistic features and then input the predicted ALVs to get F0 sequence to the decoder. Next, I'll talk about VAE. Variational autoencoder VAE is often used for latent representation learning of speech data. Vector quantized VAE for the latent space it's discrete is also popular in this field. For example, Sale et al. Succeeded in learning downsampled frame-level latent representation of F0 with Wiki VAE, and Kenta et al. Succeeded in controlling the synthetics prosody with sentence-level latent representation extracted by hierarchical VAE. In this study, we used VAE and Wiki VAE to extract accent information as latent variables by unsupervised learning. Now I'll introduce you our action extraction models. For action extraction models, we apply both a VAE and a VQ-VAE. AEM VAE learns more level action as a low-dimensional continuous representation. On the other hand, AEM VQ-VAE learns them as discrete symbols. For latent space, we adopt two-class discrete space for representing Japanese pitch accent of high-low. Since we don't provide any accent information to the linguistic features, we expect the molar level latent variables, ALVs, to represent the accent information. Next, I'll explain our action prediction models. As I described, our APMs predict molar level ALVs utilizing the accent labels of the Tokyo dialect. For action prediction models, we examine two model structures. One is APM RNN, which uses recurrent neural networks and can catch more complex features than APM DT. The other is APM DT, which uses decision trees to predict the accent latent variables. Since the accent corresponding relationships are so simple, this model can be more robust. I'll talk about the accent correspondence in the next slide. And also, we examine two kinds of input features for APMs. One is linguistic features, which does not include any accent information. And the other is linguistic features and accent labels of the Tokyo dialect. So why do we use the accent labels of the Tokyo dialect for accent prediction of the Osaka dialect? Because there are some corresponding relationships between accents of the Tokyo and Osaka dialects. The table shows one of them. This is why we examine accent labels of the Tokyo dialect as the input for APMs. For the experiments, we use two corpora. One is Osaka 3696, in which 3,696 word level utterances are recorded in the Osaka dialect by a male speaker. The other is Basic 5000, in which 5,000 sentence level utterances are recorded in the Tokyo dialect by a female speaker. We use Basic 5000 just for stabilizing the training process. For evaluation, we only used Osaka 3696. As the base model for the AEM's decoder, we adopted LSTM-RNN-based SPSS model. For AEM's encoder and APM-RNN, we use almost the same model as the decoder, but the difference is that these models output molar level features. On the other hand, APM-DT is a model that outputs molar level ALVs by decision trees. We set the dimension of the latent space to 1. We conducted experiments for evaluating our proposed models. For the experiment of accent extraction, we evaluated 3 models, including proposed AEMs, proposed AEM-VAE, VQ-VAE, and no ALV for comparison. This model predicts F0 sequence from only linguistic features. Namely, this model does not use the ALV. Let me show you the result of the objective evaluation. We evaluated the performance by F0 RMSE of the reconstructed F0 sequence. As shown in the table, both proposed models have smaller values of RMSE than no ALV, which means that proposed models succeeded in accent extraction. Also, AEM-VQ-VAE had much smaller value of RMSE than AEM-VAE, which implies two-class discrete ALV was more appropriate for representing Japanese speech accent. We also conducted an X-ray test to evaluate the extraction performance subjectively. The participants were asked which synthesized speech was closer to the original one. The result is shown in the table. As the table shows, AEM-VQ-VAE reconstructed significantly closer F0 sequence than the other 2 models. We confirmed the effectiveness of AEM-VQ-VAE also in the subjective evaluation. So we applied the decoder of AEM-VQ-VAE for action prediction and the discrete ALVs as the teacher labels for APM's training. For accent prediction, we compared 4 models, 2 kinds of the structures, 2 kinds of the input. APM-RNN uses RNN for prediction, while APM-GT uses decision trees. Here, with means that the input includes Tokyo accent labels, and without means it does not. These accent prediction models output predicted ALVs. We inputted the predicted ALVs to the decoder of BQ via E to get predicted F0 sequence. Similarly to AEM's experiment, we conducted objective and subjective evaluations. First, I'll show you the result of the objective evaluation. As the table shows, APM-RN width had the smallest F0 RMSE, which implies decision tree was not expressive enough to predict LV. And also, it can be told that the input Tokyo accent labels were effective to predict LVs of nouns of the Osaka dialect, since the improvement were biggest in nouns. Next, I'll show you the result of the subjective evaluation. The results are shown in the table. The result shows that APM-RNN width predicted more natural F0 than APM-DT, and with and without models had no significant difference. However, the difference between with and without models was biggest in nouns in the objective evaluation. So we conducted an additional X-series test with only nouns. The result of the additional subjective evaluation is shown in the table. When providing only noun utterances for the test, the predicted F0 sequence of APM-RNN with was significantly more natural than that of APM-RNN without. This implies that with appropriate model structures, the accent information of the Tokyo dialect is effective in accent prediction of nouns of the Osaka dialect. So in conclusions, we proposed accent modeling of the Osaka dialect without accent labels. First, we introduced our accent extraction models with BQ via E and showed that the proposed BQ via E model succeeded in extracting the accent from speech signals. This model and the extracted accent latent variables LVs enable to train acoustic models without accent labels. Second, we explained accent prediction models, and the results showed that RNN is more suitable for accent prediction of LVs, and the accent information of the Tokyo dialect is effective for accent prediction of nouns of the Osaka dialect. Also, the proposed framework has advantages of controllability thanks to accent latent variables, the intermediate representation. So changing the input accent latent variables would enable us to easily modify the accent of synthetic speech into more natural one. However, the value of F0 RMSE of APM-RN width is still larger than that of no LV. So we will research better model structures and representation style for more natural speech synthesis of low resource dialects of pitch accent languages. So thank you for listening.
Thank you very much. So do we have questions in the chat? No. No Japanese in online. In the audience, local. Yeah, please come. There's no stupid questions.
Hello.
Hello.
I would like to ask have you tried or consider other kind of evaluations for the pitch accent of the Osaka dialect? So as far as I know, there are certain specific pitch accent pattern, like 4 or 5 different kinds of pitch accent pattern, considering of high-low relative pitch accents in Japanese. So have you tried looking at certain classification of these patterns as an objective evaluation way instead of just evaluating the F0? And do you see something like a difference when the synthesizer gets the pitch accent patterns right? So if you have something like, I guess a hairbound pitch accent would be like the most common in the synthesizer. Do you see that a hairbound pitch accent is more commonly got right than another kind of pitch accent?
Yeah. Actually, I didn't any other evaluations for the synthetic accent of the Osaka, so definitely that will be our future work. Thank you for the question. That's so interesting for me.
You don't see any like, so you don't, but like intuitively listening to it yourself, for example, do you see like that certain pitch accent categories like Herman or Atamadakata is better than others?
Yes, maybe it's probably because of the data set, but the pitch accent of the first mora, when the first pitch accent is high, the pitch accent of the word will be better compared to when that is low. I mean,
yeah.
So you mean that there is no? I was wondering. In fact, you don't have any frequency counts of the different types of actions in your corpus. Somehow, is there any bias, in fact, in your corpus according to the frequency of the appearance of the different accents? In fact, this the frequency of the different types. No.
Yes, I would. I think I have. So I think the value of F0 is comparably higher than that of the Tokyo dialect in the Osaka dialect. The values of F0 in the Osaka dialect is a bit higher than that of the Tokyo dialect, maybe. And
yeah, okay. Thank you very much.
Thank you.
Thank you. So you have there is a question by Javier. The training data was a single word, so it's per word. So he said that the problem with Japanese accent prediction is that it has to be predicted jointly with tokenization. So do you have analyzed how it works with the synthesis of full utterances? So do you have in your prediction, do you have tokens or word tokens in the prediction?
We use full context label following the HES, and to answer to the first question, we use a single phrase which is consisted of a word and a post-positional particle, which is almost a phrase. And we confirmed that the tokenizer that transformed the text into the full context labels, that worked. If the text is kind of formatted, not if it's reading style, but if it's conversational style, it doesn't at all.
Okay. So we have time for a few questions. We are done. Well, I think yeah. So I think it will, for future work, it will be interesting to go away just from F0 errors and perhaps to know better if certain accents are realized. So to have some insights of on accent recognition somehow. So to be able to also to have expert labeling, in fact, a short part of your corpus, and to confront, in fact, the automatic prediction with expertise. No.
Yeah. Yes. Yeah.
So thank you.
Thank you.
So we have, thank you, Kazuya. So we have 2 minutes so we can wait. So yeah, it's Jason for the next talk.
Hello.
Okay.
Can you hear me?
You will place us some sound, so you can perhaps check. If,
I wasn't going to actually, but there are sounds on a link that people can listen to.
Okay. So you have a link on the web page. Okay, we can go on. Okay, so let's go on. So the next talk is about French. I'm sorry, guys. It's to awake you. So it's a liaison and pronunciation learning in end-to-end text-to-speech in French. And so the talk will be given by Jason Taylor. Thank you.
Thank you very much, Gérard. So as Gérard said, I'm going to talk to you about end-to-end text-to-speech in French. And if I could really summarize what I'm going to talk about in one sentence, it would probably be that controllability is important in pronunciation, and that potentially poses a problem for end-to-end TTS. So a brief outline of this presentation, I'm going to talk about kind of the role of the front end in TTS in different paradigms. I'll talk about this kind of issue of grapheme-based TTS and the use of the pronunciation lexicon. And in particular, not just the pronunciation lexicon, but kind of manual knowledge in text-to-speech. I'll talk about our method for evaluation, when we're using kind of graphemes or phone inputs. I think targeted stimuli is kind of more appropriate. And then we'll have a discussion about this kind of problems of G2P generalization. Okay. And I'll also talk about some of the work that I've been up to on objective evaluation very briefly. Okay, so the front end in kind of traditional paradigms and unit selection, SPSS, HMM, DNN, linguistic features are used for acoustic modeling, and they typically have some kind of manual knowledge within them, kind of a pronunciation lexicon, other kinds of modules, post-lexical modules, to actually get kind of the correct kind of linguistic structure. And then in end-to-end TTS, we have a kind of sequence of characters, and these can be phones or they can be graphemes. So if we have kind of a sentence here, we do some kind of text normalization, and then in different paradigms, the front end would kind of provide these features, and you use kind of different features for different kinds of paradigms. So in unit selection, you might attach them to units. In HMMs, you would maybe encode it in a decision tree. In DNNs, it would be in a kind of context vector. And then for end-to-end TTS, we have kind of graphemes or phones. So graphemes still run through this kind of text normalization typically. And when we're using phones, okay, some people, I think, just use a G2P model. Some people use lexicon as well. And there's a slight nuance there, which I'm going to maybe talk about a little bit more as well. So overarching questions within my research is, do phones need to come from a pronunciation lexicon? and our phones basically needed at all in TTS. So some previous work on kind of grapheme-based TTS seems to signal that that there is some help there. This has been useful. I mean, in kind of HMM TTS and unit selection, we had kind of lower intelligibility in kind of multiple papers. Although it was found that if you can increase the amount of data that you have from kind of 1 to 5 hours in Spanish, you can actually improve the intelligibility of a Spanish voice. And it's interesting that was in Spanish, because Spanish is often thought of as one of these kind of very regular, a language with very regular orthography in terms of its pronunciation. But anyway, in end-to-end TTS, we're expanding that. We typically use more than 10 hours of data. Thus, can this learning, people, I think, view it often that it's kind of on par now, this kind of the overall quality of the voice, whether you're using graphemes or phones. There is this question, right? Are phones better than graphemes in different languages? So here I've just tried to summarize different works and based on their listening test to try and find whether or not there was this significant difference, whether they use graphemes or phones. And obviously you can't really compare between the works because they're different setups, but it's interesting nonetheless. So in Deep Voice 3, we had this kind of mispronunciation test. So they kind of targeted stimuli, and they had kind of 100 words, 100 sentences, which they kind of tested directly. And then at the last SSW, we had this mushra with DCTTS using kind of gold standard phone labels. And we found a significant difference there. And then subsequent work since that time, there's been this kind of Zhang et al. And they've kind of looked at different, they used a Takatron 2 model with different languages in Spanish and Mandarin. They also found a difference, an improvement when using phones over graphemes. And this Yasude et al.'s journal paper actually looked at comparing the parameters in the encoder, and they seem to find that when you use the kind of original Takatron one, the kind of CBHG, or in their case it was a CBHL, they had kind of more parameters in that model, and they basically concluded that with more parameters you can kind of model some ambiguities within the training data slightly better, and that can lead to kind of no significant differences whether you're using graphemes or phones in the overall quality. And then these kind of more recent, this year, this Wave Takatron and EATS, these kind of fully end-to-end models that aren't using kind of a separate neural vocoder. Here, it seems that learning from phones is better. But I think that one of the key things here is that we have kind of targeted stimuli which we can actually test, and obviously there are particular parts of language, and I think this could be something that happens in lots of different writings. It's not just English, right? And we want to talk about French in a minute, but I think that perhaps the way to kind of reveal these differences is actually to look at the kind of target the stimuli, because I think when you're using kind of mean opinion scores with a mean opinion score test, like you only get kind of one stimulus at a time. So that's from one system at a time, and you can't really compare the pronunciations directly. Okay, right, so just some summary points here. So it looks like overall it's better if we use kind of a model with larger parameters, with more parameters. We have targeted mispronunciation tests that can show differences with phones. And I'm saying, should we not target pronunciation? Should we not target our stimuli to show differences between these? So what is lost without a pronunciation lexicon, and what about front-end information in other languages? So kind of non-alphabetic languages, you know, they rely on some kind of conversion to phones and other kinds of, you know, extra linguistic ideas we just heard about pitch accents in Japanese. There's also polyphone disambiguation in Mandarin. This is typically relies on kind of some form of manually extracted labels. And another point is that people will often kind of, we can frame it like this: do we use graphemes or phones? But actually, regardless of that, I think you can think of scenarios where you actually want to control pronunciation anyway. So, you know, to take an example from English, you could say, well, John says banana and Mary says banana. And to be able to show that nuance somehow. So I think you need to use, you know, you're going to need to intervene at some point. And this is, I think, a fundamental problem for kind of end-to-end text-to-speech, end-to-end in the sense of training from graphemes. Okay, so in some previous work, I've looked at kind of trying to understand the implicit pronunciation models in end-to-end TTS better. And, you know, in English, we have kind of these issues with foreign words and proper names, especially because, you know, English is a funny one because it has kind of really irregular orthography, probably more so than in French. Yeah. And there we basically found that, you know, it was better to use a pronunciation lexicon because these kind of when you implicitly try to learn a G2P model in an end-to-end system, you get this kind of frequent token bias. So if you have a word like pothole in English, that TH, that also appears in a word like the. So you get this kind of V sound. So it ends up being pronounced like pothole because the is kind of more frequent in the training data than t, h. Yeah. And you know, so a real problem here is that we're trying to generalize the pronunciations, but this doesn't actually ensure adequacy. Right. So now let's turn to French. Previous work has shown that you know that it looks like we can get kind of similar scores if we're using a kind of CBHG encoder with graphemes or phones. But this particular work, this is Perkin's work, that it's liaison. Yeah, that basically liaison was incorrectly pronounced, but both by the grapheme and the phone models. I think in this particular work, it might have been that there wasn't, I don't think an actual liaison module was used, or not a very, not a very expansive one. And that might have been like an issue with phones, right? So what is liaison? This is basically where you can insert sounds kind of at the end of words, which wouldn't normally be there. And it's kind of dependent on context, but the context that it's dependent on is kind of linguistically very deep. Like it's it requires you to kind of fully tag a sentence in terms of part of speech tags. And there's kind of lots of different rules for this. And this is normally dealt with in kind of the post-lexical part of the front end. So, for example, share on its own, this center word here, could just be share, but then in this particular instance, you'd insert a rotic, right? Mon cher ami. Excuse my French pronunciation, not brilliant. You know, do we need to manually specify this in certain cases, or just to have that controllability there? I think we're going to need a phonetic representation, right? So this is once again a problem for end-to-end synthesis. And you know, we particularly in this here we test using words which are difficult to disallowed liaison. So this is where sounds are inserted when they shouldn't be inserted, and you know, while it may not be shown in aggregate scores, maybe this is what we need the targeted tests for, right? Okay, we take these words of difficult G2P, like in English, and we take this disallowed liaison. We also did some things with I also tried some things with enchaînement because I was interested in whether or not we could use syllable boundaries. And this is basically, well, I have the stimuli here, so I can show you that with enchaînement, if you have a word like elle est danseuse, a sentence like elle est danseuse ou chanteuse, that's a kind of not a very French way of pronouncing it. you'd have to say elle est danseuse ou chanteuse. So you have this kind of syllables crossing word boundaries, and they should be pronounced together. So here for our GTP words, we have kind of foreign words for foreign names for French, and then in liaison, so this is the disallowed. So if it's les héroïnes here, so this would be bad if you pronounce this z there. It should be les héroïnes. Okay, I used a CBHG tachytron model. I used the CSS10 French data set, and I added some post-lexical rules on top of Mary TTS. And then I specified the phones because that's what I care about, is controllability, right? Okay, so we used Prolific due to the pandemic. Listeners were native French speakers. They used desktops. Maybe we can talk about this in the discussion session afterwards. I'm slightly hesitant about the confidence that was expressed in Prolific earlier. But yes, so A/B preference test. So I only used 10 sentences. It was a small listening test, but the point really was to be anecdotal here, not to kind of provide something systematic. Yes, and that's my kind of future work. I have a paper on that at Interspeech, which you should read. So preference for the pronunciation lexicon when we use these inaccurate GTP. Preference for voice with the phone, sorry, because we kind of removed these disallowed liaisons. Although this, whether or not using syllables actually helps with enchaînement is less clear here. And there are some samples at this web page here, which is provided in the paper for you to listen to. I think I'm running out of time on the on the presentation. Thus, I'll just say that, okay, so maybe in French for particular, because I think native French speakers would actually say that liaison's not that important, that most French people ignore it anyway. But I think in terms of controllability, this is something which is worth talking about. And I think French people have an innate understanding, in a way, almost innate, about what the correct pronunciation is. So they know when it doesn't sound right. Yes, so, you know, obviously it depends whether or not you can actually have the time to manually label all these things. And, you know, maybe for that reason, you're still going to use graphemes, but I think it's important. Here are the things which I made reference to earlier. I don't know if anyone noted number there. Yes, so that's my presentation. Do you have any questions?
Okay, thank you. So, is there any question on the chat? So, a specialist of French, I'm pretty sure that we do the liaison in les héroïnes. But les héros never has the liaison, which is a good point.
Yeah.
So
okay.
Going along.
Okay. I mean, I obviously took these examples from kind of a guide that said, you know, this is a word where it shouldn't be pronounced. But yeah. So I think, but I actually think that question probably reflects what I was saying earlier, right? That for French people, liaison is not something which is necessarily that kind of strict in a way. Yeah. So I think, but you know, at the end of the day in France, you have this kind of academy which says that this is how it should be, right? So, you know, it's a kind of prescriptivist organization. So, you know, I think that is.
In fact, so I'm French, huh? So you can guess it. For example, if you take this example of R, manger à la maison and so on, so final of the infinitive. It's really depending on the style. For example, I studied free readers of audiobooks. And it's very variable, even in the same, for the same speaker, depending on the content of the book, especially the period where the book has been written somehow. So depending, it's the 18th century, the 19th century, and so on. For example, Nadine Eckert-Boulet, she sometimes performed a lot of air liaison to signal it was the bourgeois society, well-educated, and so on, and doesn't perform this R to signal dialogue where you have people from low class, for example. So
right.
It's really a question. And of course, it has an impact not only on liaison, but also on prosody in general. So, I think for myself, at least, I think really the liaison is part of a style information. So if you have a style component like a GST or whatever, a VIE and so on, which is able to somehow bias the output of the encoder that decides how the phonetic implementation, in fact, of the phonological units. Normally, the liaison should be part of this decision. That's my guess. But,
yeah. Obviously, I haven't done an experiment with a VAE or anything like that here. But my experience with dealing with kind of sequence models is that, it doesn't necessarily focus on things like that, right? It can be quite random in a way. So in particular with liaison, right? So it kind of randomly inserts these sounds in some cases, and then in other cases it doesn't when you're using kind of graphemes or something. Overall, right, the argument that I'm making is that you want to have control over these kinds of things, and for that reason, you want to have a kind of phonetic representation.
But just remember that the liaison signal, in fact, to the audience, the mastery of the language. So, for example, Chirac was well known to perform forbidden liaison because he was the president of a republic. He knows about the liaison, and he allowed himself to produce a forbidden liaison. So, in fact, by this liaison, you indicate the level, the social level in the society. So it's a strong social marker. I suppose that, for example, the degree of articulation of the R in Britain signal also this kind of social status. So yeah, again, I think all these things are part of the style of, and I think liaison or all these phonological phenomena, epenthesis, schwas, and whatever, is really part of a strategy of communication where you show, in fact, implicitly the mastery of a language or your social status somehow. So extracting, in fact, G2P from prosody, from other components of, I think it's my opinion, it's dangerous, but I don't. So, sorry, yeah, okay, another point. Please.
Hello.
I think it's really interesting, and I totally agree with you that it's really important that you can have control over those kind of things. I was thinking about a similar thing in English where you do the R linking, or someone might say Amanda or something, or someone's name. And I just wanted to say, I think it's really good that you, instead of just doing overall MOS tests, that you can hone in on specific aspects of pronunciation that show like it's almost like a human speaker. So
yeah, I think given that people say Tacotron models with neural vocoder is kind of human-like, I think we should maybe analyze it like this perhaps.
Now that I think about it, the other thing that I think is really important is when you have the labels of your training data, that they actually also reflect what is being said. And so there are some rules in English where sometimes you say the word to with the u sound, and sometimes you say te with the schwa. So if you don't have the different phoneme labels and you just throw it all into your system, the model will have some kind of muddled representation for that sound, and
and I think
you can't really distinguish that.
I think in earlier paradigms, right, kind of HMM or unit selection, where you know, like a Festbox voice, where you have kind of an hour of speech or 2 hours of speech or something, it's feasible to sit there and kind of listen and label everything. But once you start using ever more data, this problem, it kind of, I don't know, it's very expensive to.
No, it is. But if there are some rules underlying it, then you can kind of predict when one version is used over the other, possibly.
Yeah, and obviously I noticed that yesterday there's kind of these papers on kind of multilingual things, and I think there's a question there over kind of what representations one should be using.
Right.
There as well, and also in other languages, I think. So kind of English, French, Mandarin, Japanese, they kind of have quite old writing systems. And obviously, I think kind of lower resource languages typically have a kind of, you know, linguistics, kind of phonetic transcription, and that is their orthography anyway. So there's always that question, but I always think that there's kind of more information within a, like we were saying, like Gérard was just saying, you know, liaison is stylistic.
Right.
You know, you need that kind of in-depth knowledge of the language to understand that in a sense, you know, and I think with these kind of low resource languages, we don't necessarily understand that. So, because you know, it's a matter of expertise.
Right.
Yeah.
Okay. Anyway.
Thank you, Esther.
So we can discuss with Javier about commercial. Anyway, just to mention, in the CMU DIC, the English determinant the is the. So even the labeling of the old Arctic A database, all the were labeled the, even when it's the.
Oh, right.
Okay.
That's interesting. Well, yes, I don't actually use the CMU.
Arctic, you have. I'm not a very fluent English speaker, but there are some errors in.
I don't actually use the CMU DIC in my research for English.
People from CSTR here. So okay. So we have plenty of time because, in fact, the next presentation, the offer didn't register. They don't show up, so we just have a video. So we will play the video. We can perhaps have a small discussion. But if you think that it's the right time for having a discussion, I think your presentation is somehow very stimulating. But you know, yesterday, I don't know if you were there, but I was trying to trigger a discussion about this global trend of postponing, in fact, the end-to-end to
I was thinking about that over dinner last
features.
night. Yeah.
so it's the same question here.
Yeah.
Because who decides which variance is interesting, and this should be, I think, as I said, it should be coherent to the prosody, to the if you want to show the mastery of a language. And I think there is an insight in commercial products. If you're addressing to a child, an elderly person, which is low class or high class, well-educated person, and so on. So of course you don't have the same way of pronouncing silences and so on. So you need a really a social component in your style. So reference encoder, what you are using. I think transcription G2P is part of this strategy.
Exactly, and I think it's often overlooked. I think if you kind of look overall at kind of end-to-end papers, I kind of read them. As I read them, I noticed that there's kind of text normalization is almost done, but it's almost not acknowledged by the authors in a way, because it's not the focus of whatever they're writing about, right? They're focused on improving the acoustic model in some way or something like this. I think you're exactly right. This is a challenge, and I think the way you would traditionally do is kind of using appropriate data, right? Use data of a particular social class, say, or a particular dialect or something, and but that's maybe not necessarily an efficient way to do it. And once you're in this kind of space where you're dealing with kind of multiple speakers, what happens there? I mean, my work isn't on multi-speaker TTS, but I know, for example, in English, you have this these metaphonemes, this keyword phonology, which kind of goes beyond the level of kind of the phoneme. It goes kind of beyond another extra level, which is kind of a metaphoneme, which is where you kind of describe different dialects with kind of a keyword. So, for example, a word like the car Mazda, like the Mazda car brand. That in English is kind of in my accent is Mazda, but in certain American accents it would be Mazda. So you kind of describe variation depending on these keywords. Now I've tried doing this in English with kind of end-to-end models with Takatron, and what I found was that in the training data for something like LJ speech, there isn't actually kind of enough counts for some of these metaphonemes to actually within LJ speech, and that's quite a large corpus. So I think part of it is actually also looking at kind of when you not just using more data, right, but actually selecting the data in some way to kind of be encompassing of kind of different variants and things like that.
No, it's quite messy. For example, ananas. I think 50% of French people will say ananas, and 50% ananas, because they want to show up that they know that
exactly.
ananas is finishing with S. But there are a lot of examples like this. My town is Ebin with an S at the end. So 50% Ebin, 50% Ebins. So when you do an inquiry as a commercial system, how you pronounce your city, even the people inhabiting the city are not, so depending on the area of the city you are living in, you have a different pronunciation. So it's a strong marker. As I said, it's a strong marker. Kut, yes, it's the same for Alexis, ku et kut. Just to show up that you know how it's the right orthograph. Perhaps it will disappearing because young people are very bad at orthography now. So out, but out, I think it's nobody is pronouncing u. So anyway, oh, you do.
I think I'm on a wider point just on kind of end-to-end synthesis. I mean, we could argue that we're only just starting to see end-to-end synthesis now, right? This kind of fully end-to-end, this kind of single, so you kind of have one model and that's what you train. I think we're only really starting to see that kind of in the past year. I think there's another video too.
So we are, please.
So if you are speaking about variability, then I would call your attention that there is also in third person variability as well. And the problem is that usually the output of most TTS systems is deterministic. So if you input something, you always get the same if form if you input it like 3 times. Maybe, and that I think this is one of the reasons why we get bored for a longer thing. Somehow we feel it. Yes, sometimes there is some random change of some parameters, but that is usually not even noticed. Or if you do it randomly, then if you notice it, then it will be wrong. So it's a very interesting question of, like as humans, you never say like goodbye twice the same way, exactly the same way. You will never get the same waveform. So for me, it's a big question of how to implement it in a good system. I know it's different from the one that we were talked about before, but if we speak about variability, I think this is can be a key point also commercially for larger applications where people tolerate text-to-speech for more than 2 minutes. So that would be an interesting test, actually, that to use to set up a test where you play various lengths of examples for TTS systems and then wait for when people get bored. So, we can go to the next one.
Okay, guys. So normally we have this video. I suggest we can play it right now. If you have some comments or if that's triggering discussion without the offers, it's could be interesting. So could you play? Yeah.
Hello, everyone. I'm honored that our paper can be received by the Speech Science workshop, and I'm honored to be able to participate in this conference and make a presentation. The paper name is Phasor TDS, Robust and Efficient Attention-Based Neural TDS. In this paper, 3 parts of work are carried out from the acoustic model and improving the robustness of the TDS acoustic model and the speed of senses. Our acoustic model framework is based on Takamichi, as shown on the right. Next, I will specifically introduce the background and the content of the paper. The first is the background and the motivation. First of all, the location-based mechanism, attention mechanism proposed by Google has achieved very good performance, but it still has some problems. Among them, the attention calculation distribution alpha is calculated from the mixed Gaussian distribution of key Gaussian components. Although each single Gaussian component is monotonic, the center of the gravity of its mixed Gaussian distribution is not necessarily monotonic, which will collapse the alignment and reduce the robustness of the model. On the other hand, Takamichi with stop token loss will have the problem of stop early and the problem of stop early will occur. In order to solve the above problems, we have mainly done 3 parts of work. First, we propose a Gaussian attention mechanism. We propose to use a single Gaussian to model the alignment distribution, and the monotonic of the alignment is ensured by making the mean change delta is non-negative. Among them, the physical meaning of the mean and the variance of the Gaussian distribution is that the mean controls the position of the attention window, and the variance controls the width of the attention window. Intuitively, at the end of the sentence, the mean value should align of the text. Therefore, we propose the attentive stop loss. Attentive stop loss ensures the completeness of the attention mechanism to improve the robustness of the model. In addition, in order to speed up the synthesis, we carried out bit pruning on the two-layer LSTM in the model's decoder and accelerated the synthesis speed by gradually abating the target sparsity of the model parameters and used the PF16 data format. The final model losses consist of three parts. The first two parts are the spectrum reconstruction loss before and after postnet, and the third part is the proposed attentive stop loss. The third part is experiment and evaluation. The first is the mean opening score, as shown in Table 1. The single Gaussian attention mechanism can achieve a natural degree similar to the GMMA2B attention mechanism. In addition, the main idea of this paper is to improve the robustness of the model. Compared with the GMA2B attention mechanism, the world error rate of our post model has dropped from 4.1% to 0.9%. Moreover, on a single core CPU, our sparse model can retrieve 35 real-time, and the PF16 format model can retrieve about 60 times faster than real-time. Finally, there is a demo of model synthesis.
动结束了，这次运动了35分钟，距离4.5公里，平均配速7.2。下次运动再见。春眠不觉晓，处处闻啼鸟。夜来风雨声，花落知多少。啊哦啊哦哎，阿斯德啊斯德，阿斯德洛德洛德，阿斯德啊斯德洛德，啊哦啊哦哎。 阿斯德斯德，阿斯德洛德洛德，阿斯德斯德洛德。倒计时20秒钟，19、18、17、16、15、14、13、12、11、10、9、8、7、6、5、4、3、2、1、0。
My presentation is over. Thank you for listening.
So, any comment from Chinese people? So, or comments on this model? I don't understand how they have three systems and all the three systems are 4.31, 4.32, and well, and so on. We are missing a low anchor and a high anchor. So, any comments from through the chat? The room, local. So I think we can close the session. And so exceptional, I was wondering if there was a metric on how many early stops were fixed. We are wondering also, we are sharing your concern. Okay. So we have extra time for lunch or for this break. So Geza, see you this afternoon here at no? Ah, the keynote is coming. Oh, that's why I did. Oh, it's coffee time. Ah, it's coffee time. Coffee time. Okay. Okay. Small. Okay. Okay. So see you in what, 10 minutes?
Yes.
11:10. So a quarter of an hour. Okay, guys.